in this video, we're going to focus on approximation using differentials. First, let's discuss the difference between derivatives and differentials. When we talk about derivatives, they are denoted usually by dy dx. This is if we have a function y equals f of x. And this notation, we treat this notation as a single symbol, all right? The derivative of y with respect to x. Now we can also interpret this notation as the ratio between dy and dx. So this time, we will be treating dy as a separate expression from dx. We call them the differentials. Okay, dy is the differential of y, and dx is the differential of x. Okay, so let's recall if we have y as a function of x. If we take the derivative of y with respect to x, that's dy dx equals f prime of x. Now, if we are only asked to find the differential of y, then what we do is just isolate dy, multiply both sides by dx to find or to get the differential of y. Okay. So again, if we have y as a function of x, if we are asked to find the differential of y only, then that's dy equals f prime of x dx. All right. So the difference here is that dy is separated from dx. If, for instance, dx is required, then you just isolate the differential of x or dx. Okay, so these are differentials. For instance, if we are given y equals x squared, if we are asked to find the derivative of y with respect to x, then that's dy dx, right? And it's equal to 2x. However, if we are asked to find, for instance, the differential of y only, so that's dy, then this is equal to 2x dx. Okay, if we are asked to find dx, then that's dy over 2x. All right, differential of y, differential of x. Okay, one of the applications of this concept, the differentials, is approximation. Okay, so let's talk about approximation formula. Say we have a function y equals f of x. Since y depends on the value of x, therefore if there is a change in x, then there's a corresponding change in y. Okay, and it can be represented through this equation. Okay, again, if you have a change in x, so that's represented by this expression here, delta x, then there's a corresponding change in y. Okay, if these changes are very small, then we can express delta y and delta x as dy and dx. This is now our approximation formula. We'll see later how this approximation formula works. Okay, or since y is f of x and dy, as I mentioned earlier, is f prime of x dx, then we can rewrite this equation again in this form. Okay, so f of x plus dx equals f of x, which is y, right? And then f prime of x dx, this is equivalent to the differential of y. So this is another form of the approximation formula that we can use. Okay, so let's look at some examples. First problem, we are asked to find the approximate value of square root of 17 using differentials. Now, if we just plug in square root of 17 to our calculators, we'll get approximately 4.1231. So for this problem, we will be using differentials, and let's see if we get approximately the same value. Okay, so again, this is our working equation, the approximation formula. The first step is to let square root of 17, this is what we are asked to find the value of. Okay, let square root of 17 be equal to the approximation formula. Okay, and the next step is to take out the operation involved. In this case, the operation involved is taking the square root of a number. Okay, so you take out the operation, which is taking the square root, and then we'll focus first on the value or the radicand in this case, which is 17. Okay, and then equate this 17 2x plus dx, which is this one. So you take out the operation involved, the function, which is taking the square root of, and then focus on the value under the square root, so x plus dx. Okay, and then the next thing that we need to do is to find a value for x for which we can conveniently apply the operation involved in this problem. So again, the operation involved here is taking the square root of a number. So for this problem, x should be a perfect square number so that we can easily take its square root. And number two, it should be the nearest perfect square to 17. Okay, so that we can make dx as small as possible so as to get the most accurate approximation. Okay, so nearest perfect square to 17 is 16. Okay, therefore x is equal to 16 and dx is 1. Okay, 16 plus 1 is 17. Alright, now let's proceed to the next set of steps. This time we'll focus on the operation involved in this problem. Okay, again, the operation involved is taking the square root of a number. Let's make an equation out of that operation. So we can represent the operation involved as y equals square root of x. Again, because we want to take the square root of a number. Alright, so we now have y equals square root of x. Let's take the differential of y. We now have dy equals dx over 2 square root of x. And then let's isolate this equation. Square root of 17 equals y plus dy. This will now be our final working equation. Okay, and then substitute the equivalent expressions for y and dy. Y is square root of x, dy is dx over 2 square root of x. And then substitute the values for x and dx. Okay, so you already have identified what's x and dx previously. Okay, plug in the values, x is 16, dx is 1. Okay, and then evaluate. Square root of 16 is 4. Again, square root of 16 is 4, so this will become 1 over 8. And then 4 plus 1 over 8 will give us 33 over 8. And this is approximately 4.125, which is approximately equal to 4.1231 if using the calculator. So this is now approximation using differentials. Next, let's try this one. Approximate the value of cube root of 26.5 using differentials. Again, let's try first using calculator. It will result to 2.9814. Okay, so let's try and see if using differential will give approximately the same value. Okay, so working equation, the approximation formula, and then first step, let cube root of 26.5 be equal to the approximation formula. Okay, and then again, we'll focus first on the value 26.5, equate this to x plus dx. This time, the operation involved is cube root, taking the cube root of a number. So x should be a perfect cube, right? So that we can easily take its cube root. And it should be the nearest perfect cube to 26.5. So nearest perfect cube to 26.5 is 27. Okay, cube root of 27 is 3. Therefore, we can let x be 27. To get 26.5, dx should be negative 0.5. Okay, or negative 1/2. Alright, so next, let's make an equation out of the operation involved. So again, this is taking the cube root of a number. So we can represent this as y equals cube root of x. Okay, and then take the differential of y. This will give us dx over 3 cube root of x squared. Okay, then next, let's focus on this equation. Alright, this is now our final working equation for this problem, cube root of 26.5 equals y plus dy. Then plug in again the equivalent expressions for y and dy. Y is cube root of x, dy is dx over 3 cube root of x squared. Plug in the values of x and dx. This will give us cube root of 27 plus negative 1 half divided by 3 times cube root of 27 squared. Alright, so cube root of 27, that's 3. Therefore, cube root of 27 squared is 9. Okay, 9 times 3, that's 18, times 2, that's 54. So we have 3 minus 1 over 54, and this will result to 161 over 54, or approximately 2.9815. And it's approximately the same as the one that we obtained using our calculator. Alright? Next, let's try this one. If y is equal to x raised to 5 minus 2x cubed, find the approximate value of y if x is equal to 2.01 using differentials. Okay, so again, let's try first using our calculators. Plug in 2.01, so we get approximately 16.5668. Let's try using differentials. For this problem, we will be using the other form of the approximation formula, which is this one. F of x plus dx equals f of x plus f prime of x dx. Alright. First step for these kinds of problems is to let whatever is the given value for x be equal to x plus dx. Okay. And then choose a value for x that is nearest to 0.01 that will allow us to conveniently evaluate y. Okay. So in this case, obviously, it should be a whole number that is nearest to 0.01, and that is 2. Okay, so let x be equal to 2. To get to 0.01, dx must be 0.01, or 1 over 100. Okay. Next, let's focus on the given function, y equals x raised to 5 minus 2x cubed. Okay, remember that y is equal to f of x, so we can rewrite this equation as f of x equals x raised to 5 minus 2x cubed. Alright, where f prime of x is, of course, it's the derivative with respect to x, so that's 5x raised to 4 minus 6x squared. And then going back to the working equation, f of x plus dx equals f of x plus f prime of x dx, where x plus dx is 2.01, right? So f of 2.01 equals f of x is x raised to 5 minus 2x cubed, right? And then f prime of x here is this one, 5x raised to 4 minus 6x squared. And then times dx. Okay? And then next, we plug in the values that we obtained earlier for x and dx. Okay? So x is 2, and then dx is 1 over 100. You just simplify this expression on the right. We'll arrive at this value, 414 over 25, which is approximately equal to 16.56, which is also approximately equal to the value that we obtained using our calculators. Okay, so this is now our final answer. Next, find the approximate surface area of a sphere with radius of 5.02 inches. Again, using differentials. Okay, so let's try first without the use of differentials. Surface area of a sphere, the formula is 4 pi radius squared. Plug in the radius, 5.02. Using our calculators, we'll get 100.8016 pi square inches. Okay, and then let's try using differentials if we get the same or approximately the same value. Okay, So in this case, the surface area is a function of the radius, right? So our working equation can be uh, written in this form. Okay, instead of y as a function of x, we have here the surface area as a function of the radius r. Okay, so instead of y plus dy equals f of x plus dx, we'll be using uh, the quantities that are involved in this formula, the surface area and the radius. So we have SA plus dSA equals f of r plus dr. This is our working equation for this problem. Okay. First, let the given radius 5.02 be equal to r plus dr. So similar to what we did in the previous problem, we have to identify a value for r, a whole number that is nearest 5.02, and that is 5. Okay, so r is 5, and to get 5.02, dr should be 0.02, or that's 1 over 50. Okay. Then going back to the formula for SA, or the surface area of sphere, we have here SA equals 4 pi r squared, and then taking the differential of SA, all right, that's dSA. So we have here 8 pi r dr. And then using this equation, okay, f of r plus dr equals SA plus dSA, all right, where r plus dr here, r plus dr is 5.02, so plug in 5.02, right? And SA is 4 pi r squared, dSA is 8 pi r dr. All right, so plug in those values and equivalent expressions. This will give us f of 5.02, which basically means find SA where r is 5.02. Okay, this is equal to SA, where SA is 4 pi r squared, and then dSA is 8 pi r dr. Then from here, we can actually plug in immediately the values for r and dr. We can also simplify by factoring out the common factors. So we have here 4 pi r, and then times the quantity r plus 2 dr, and then plug in the values for r and dr. All right. So r is 5, dr is 1 over 50, and then simplifying will result to this value, 504 pi over 5, which is approximately equal to 100.8 pi square inches, right? Which is also approximately equal to this value here, which we obtained by directly substituting or plugging in 5.02 to the formula for the surface area. Okay, so this is how we approximate values using differentials.